and welcome back to QGIS. This is the third week of tutorials, and this week for QGIS we have two interesting tutorials. First, we'll look into cartograms. What are they, how you can use them to your advantage, and when you should maybe use them, and how to create two types of maps with QGIS cartograms. And then we'll look into a specific type of line map, which is origin destination map that become very crowded very easily. So we'll think of ways how we could make that kind of map more readable. So first, cartograms. This type of map is probably very familiar with it for you. It's an electoral map that shows the popularity of candidates, in this case in the US election in 2012. Now, a quick reading of this map, a quick peek, you might end up with the conclusion that, okay, this red candidate won with a landslide. But that's not actually what happened in the election. The blue candidate, Barack Obama, won. So how come? Well, that sort of visual first impression comes from the fact that, obviously a lot of the map is taken up by these red areas. So how could we actually, but that's not what's the most meaningful thing in an election. The most meaningful thing is where are those people who, like how many people vote for a candidate. And obviously in this case, there's other factors, but in any case, we need to somehow capture that phenomena and not just sort of this raw spatial distribution. So we need to say something about number of voters per administrative unit, which varies quite a lot between these areas. So area is always does not equate importance, at least for this phenomenon that we want to map. So this has been a problem for quite a long while, and there are approaches to mitigate this, and one of them is cartogram. So where we sort of distort this physical space in our favor to sort of emphasize a certain factor. For example, we might emphasize, in this case, the number of people per electoral district. So in this tutorial, you will learn how to make non-contiguous and contiguous cartograms. And if you're interested in more examples, you might link to this excellent article by Kenneth Field that introduces both this and this idea behind cartograms and these both types of cartograms and more that we can't really do in QGIS easily. But I recommend you take a look at this if you're interested in the idea. So let's get to the actual tutorial. So for this, you will need two plugins installed. One of them is called Cartogram Tree, which is a tool for creating these contiguous or continuous cartograms. As always, you can find both of these from the plugin repository. So Cartogram Tree should be there. And then for this non-contiguous cartograms, we'll need to modify or scale up the geometry somehow. So for that purpose, we need this plugin called Shape Tools. So do install both Cartogram Tree and Shape Tools. For this one, for data, we don't actually need anything external. We can just we use the example dataset from Cartogram Tree plugin. So once you install it, you can find it under Vector and Cartogram, and there's this drop down menu called Add Sample Dataset. So this adds a nice map of Austria, which we'll use for our examples. And I guess the first thing to notice here is that we now have a non-optimal coordinate reference system, so projection for this area. So we can check which one was the, okay, so the native coordinate reference system for this one is 31287. So let's select that one. Lambert. Yeah, it looks to be a good one to use over the whole of Austria. Yes. So one thing I guess to notice here immediately about Austria, this sample dataset has a nice default visualization. It shows, so actually let's first check out the attribute table. So what you have here is population in 2017, and then you have area in square kilometers. So these are NUTS regions, which is a statistical sort of definition of areas over the whole of Europe. So you have population, you have the area by square kilometer, and then it's visualized by this population density. So I guess the big thing to notice here that population density varies quite a lot within Austria. So there are these regions where population density is really low in comparison to Vienna, so the capital region, which is also like small in this region delineation, and it's really highly populated. So then if we were to map some sort of phenomena, like let's say again electoral map of Austria, so then even though Vienna area has quite a lot of impact on the outcome of these elections, then it actually isn't emphasized very well. So if we were to create now a non-contiguous cartogram, so this is a really simple one. So we're relying on this definition by Olson already back in 1976, where it was defined. So we have this scale factor that's defined here. And what we need for it is some sort of value. So a value could be, if we want to map some values thing that we kind of want to use to scale this whole thing. So in this case, we would use population, but of course it could be some subset of certain population. It could be like male population, or it could be something completely different. It could be like metric tons of carbon emissions, for example. So you could think of course, beyond population. Then we need area in some sort of variable of the place that we're mapping. So, okay, for example, take square kilometers. And then we need something that we will scale everything else in relation to. So how much larger or smaller is everything else? And this is called an anchor unit. It's this value k here. So the anchor unit will stay the same size while everything else is scaled relative to it. It's good to choose an anchor unit that has like a high density, because otherwise things will get scaled up and then they'll get overlapping. So in our case, we'll use Vienna as the anchor unit. Okay, so we need to create all of these variables. First, we'll open up attribute table and then field calculator. So we'll add this column called population density squared. Square it so to make the differences not as dramatic as they would otherwise be. So this takes the population of the population column, and then it takes the area column. It divides it, so we take just the density of this phenomena, and then we square that value. And then we get something like this. And it will be like this is Vienna, so it's going to be the highest one. And then we'll need to calculate this scale factor. And for that, we decided to use Vienna, so we'll take the maximum value of population density squared and then times it with population density squared and then divide all of that by 1. So I'll show you what that means. I could remember to change the field type to decimal, otherwise it's rounded to integers. So if you use this expression, so then we get this scaling factor that tells that, okay, if Vienna here, we don't scale that at all, we keep that constant. So then we'll actually reduce this area. Yeah, that's the second highest population density. So we will reduce that to about 1/5 of what it was. And it's the same applies to all of these. The lower the population density squared is, so then the harsher the scaling will be. Okay, so now we actually have everything that we need for calculating this non-contiguous cartogram. So we'll use a tool called geodesic transformations from the plugin shape tools that we installed. And with this, we could do all sorts of nice transformations for our layer. We could scale them, translate them, everything, rotate them. We'll use this scale factor about the centroid. And instead of setting a static scaling for all of the features, we'll say that use this scaling factor column that we defined earlier. That you can just run it. And now you have the sort of output. So now everything is scaled in relation to the population density, and Vienna has a population count rather, and Vienna has stayed the same, whereas everything else has shrunken quite a bit. So now the question would be that how could you visualize this if we remove everything that's sort of giving us an understanding of the geographical shape? Then actually this looks pretty nonsensical. It doesn't look like Austria anymore. So then this is a pickle. One approach could be that, like I have done here, an example. So for visualizing this non-contiguous cartogram, I've kept the background of Austria in there. And then I added this inset maps that shows which region corresponds with each scaled region here. And I can quickly run you through that process, not to make the whole map, but just to give you maybe one idea of how we could work with these non-contiguous cartograms. So we need to add another layer, another sample data set, because we need 2 of these. Then we can say that this is the background Austria layer. Then we can just make it this kind of static single color layer, something like that. A little bit there, yeah. Because I'm lazy, I'm just gonna add some opacity to make all of these edges a bit not as aggressive. We need also our sort of a reference map here. For that, we can just set categorized. And now, if we were to map some sort of phenomenon like the electoral districts, we would need to sort of set it here. But instead, because we are just mapping, we're not at this point mapping any actual phenomena. So we'll just set these nuts to regions so that every region will have a unique color. Yes. So then all we have to do is make sure that these colors here match with the transformed layer. So you can just copy and paste the style or the symbology. So now they match. And then do the magic in print layout. Choose set of maps. Now always if we want to make changes to your map, so we can lock the layers here. If you want to sort of make changes to another map rather, so you have to keep some of this static, so you can lock the layers. So then it keeps what's visible here at the moment. And then we can change what's visible here at the actual working area. Now he updated. So now we have this. Good. So now there's some sort of connection between these 2 maps. Yeah, so that's one approach. But obviously, this sort of long QGIS map isn't very visually pleasing. It's not really a great approach, I don't think. So because we lose sort of topology between the areas, and then we also lose really a lot of the interpretability of the maps. So there's another approach that we can try out in QGIS. It sort of keeps all of the neighbors, but doesn't keep the shapes of the areas. And with this we can create with the cartogram tree program. It's nice, you can just run it here, compute cartogram, and make sure to select the correct layer. And we'll use the population to distort it. And here are some conditions that sort of the algorithm uses. So max number of iterations is 10. That's the minimum that the plugin creators suggest. This is the max average error. So how far away from optimal solution it will be. So if you want to have more accurate solutions, so then you can keep it running for longer, but we'll just keep this default settings. And you can run it. It's going to take a while, so let's return once it's done. Well, actually, it's done. A lot of it has stayed the same, yes, but now you can see that this fun, really huge distortion around the capital region, which we expected because that stands out so much in the case of Austria. And with this, you could do a map like I showed you before. Insert map there. Lock these layers. And just have this loaded version that we have here. Yeah, something like this. So it's not, we could like maybe rather than having this another normal map here, we could maybe label these areas. We could draw lines between the areas so that people know which match, but I think it is a serviceable approach. So this you could use in your advantage. Now, the next step, of course, would be that we have some sort of interesting phenomena that we actually map, be that like electoral most popular party or something. So we could use these cartograms either as a way as they've been used in this wordmapper.org. So this interesting site that has a lot of these different maps. And they use it, for example, to map the number of Olympic medals. So we could use that sort of distorted geometry as itself as the map. Or then we can distort by population or some other variable, and then have some sort of categorical variable that we want to map. I still have a small discussion of what actually are cartograms. So you need to run these, and I don't think I will run them either. But here I sort of calculated for the contiguous cartogram that I was just created, I calculated a new population sort of portion or share distribution, and then the area of these distorted areas. Yeah, distorted regions rather. And then you will get something like this as your outcome. So how much of the total area of Austria is covered by this newly distorted regions? What is the proportion of population of Austria that lives in these regions? And then what's the difference between those two values? And what this actually tells you is that these are quite close to each other. So that's actually the sort of goal of this algorithm, to make these variables as close as possible, while sort of keeping still the regions somehow understandable. It's off by a few percentage points. Maybe if you run it longer, it might get closer to that goal. But yeah, so thinking of the diagrams. So if you remember, cartogram is a sort of combination of maps or cartas and then diagrams. So there's this nice quote from worldmapper.org that says that cartograms are best understood as pie charts, where the segment of the pie is reshaped to look like a country. So if you think the cartograms from that angle, then it makes sense that this portion of the population is almost the same. So think of this as a kind of map shape, kind of matching to real world shapes pie chart. And then if you think of pie charts, they have their people who like them and then people who really, really dislike them. One problem with them, I think, is that when we have many variables, so then one sector of the pie can be really small. That becomes rather unreadable. So our cartogram works really nicely for Austria at this NUTS2 level because there are so few regions. But if we were to create a cartogram, for example, of the 309 municipalities of Finland by population, so you can see the outcome here in the instructions. So what does this tell us? Well, it maybe tells us that there's a really high sort of south-north shift, like in terms of population density. There are a few big cities in the south and a lot of less populated areas in the north, even though there's a lot of area there. But in terms of matching sort of one region to another, you probably can't do it. Like it becomes really unusable for that purpose. So think of these things as you create and use your cartograms. What would be the correct number of regions to use it for? Does this tell about the phenomena that I'm presenting accurately? Maybe if you want to just show this imbalanced distribution of population in Finland, then this is a good thing. You want to show something at the municipal level, some sort of phenomena, so then maybe it's not a great solution, at least it's contiguous cartograms. And I mentioned this really nice article earlier about cartograms, so there are, of course, many other ways to make them that might suit your purpose better. So graphical or gridded cartograms, where this phenomena instead we sort of move even further away from the actual physical areas and shapes into something more abstracted, but something that might be more informative. Unfortunately, there isn't really a great way to make these as of yet in QGIS. For example, this drawing cartograms where the shapes are replaced with, where the areas are replaced with these circles of varying sizes. So that this would be nice to make, but unfortunately I'm not aware of any tools to make that in QGIS at the moment. There are some links at the end of this article where you can, where some alternative or like ways to do this, these maps in other tools are suggested. So if you're interested, please take a look at those. As always, if you want to replicate the processing flow of this notebook, you can run this model that you can find from the QGIS files. The next part of this tutorial concerns origin destiny mobilities, how you can visualize those, and how you might use edge bundling as one approach for making these cluttered maps more readable. So what is OD data? So it's origin destination data. That's basically a very abstracted form of sort of movement tracked between two places. Have we already actually used this type of data previously? Like in week two, we plotted these mobilities between, or these connections between two airports. And you check this Python tutorials, you can also find an example there. So this is the minimum amount of information that you need for a trajectory. And it's quite common to find this if you look for mobility data, so it might often be OD. One problem with these for cartographic purposes is that they become very quickly very cluttered. So if the idea is to show in a larger scale where people move from which place to which place, so then you might end up with this kind of what Porthus calls in this linked article a hairball visualization. So this is an example of this week's tutorial data with no visualization. And there isn't even that many data points in this. So it's only some 500 lines. And even that doesn't really tell us much in terms of like where are the big sort of amounts of mobility is moving from, where the places where those connections are or where they are not, which of these sort of 3 places, destinations here that are visualized is the most popular, for example. So this is already a quite small snippet of data, and it still has some issues for visualization purposes. So we look at 2 approaches, as I mentioned. We'll try to fine-tune the symbology to make this more readable. We can get quite a lot of village with that way. And then we'll actually transform the geometries themselves, sort of bundle them together, the geometries that go towards the same location with this edge bundling tool. So as prerequisites, this tutorial, you need to download and install a plugin. And this is a bit different from the earlier ones because this plugin is not publicly available in the QGIS official plugin repository. It's installed from the GitHub pages. So it's originally provided by Anita Grasser in her paper that's linked to here. And I have made a small modification to enable it to run on modern versions of QGIS. So that's why I need to provide it like this. And you will find it in the week's QGIS files. So processing edge bundling.zip. So it's a zipped file, a folder rather, that has all of the elements needed to install it. So download it. You should have it if you have all these QGIS files already. Then you need to install it from plugins, manage install plugins from the kind of normal way. But then actually you need to select this install from zip. And from here, you should navigate to the path where you have it, where you have the sort of edge bundling zip file, and then install plugin. And with that, you're good to go. And what this does is adds this edge bundling tool in the processing toolbox, cross-directed edge bundling. And we'll use that later on. So the data that we're using to get this sort of OD connections is 2 mobilities in the Erasmus project in the European Union at the level of statistical nuts to regions. So again, same as the first part of on the cartogram tutorial. This data is being processed and provided by researchers at the Digital Geography Lab at the University of Helsinki, at the Multidin project. If you're interested in this data, you can find the full dataset is linked here. And there's the data description paper that sort of goes into more detail of how this data set has been processed and sort of prepared. But we will use a small excerpt of it from the year 2018. So Erasmus mobility data geopackage. And as always, you'll have the basic style files and processing model file in the QGIS files. So let's get to the tutorial. So we should start by adding the dataset to the project. Drag it from whenever you have it. You will find 2 layers in this geopackage. Erasmus mobility data. One of them is just used for labeling. It's the point file. And the other one has the actual data that we're interested in. Always, it's a good habit to check out the attribute table. And here you can find the origin, the sort of unique code that identifies this nuts to region. The first part indicates the country, and the second part is, I guess, unique for that country. and then there's a equivalent one for the destination. And this data has been filtered to only include destinations to the 3 most visited NUTS2 regions in Germany. So why I did this pre-filtering is that this edge banding tool is actually really slow. If you use any sort of larger data sets, then it becomes infeasibly long to sort of for this purpose of this tutorial. So keep that also in mind that these tools can be quite expensive to run. But yeah, it has Berlin, Köln, and Oberbayern destinations in here. And then there's this origin destination ID that sort of combines these two to one field. So first we want to just sort of emphasize the connections that have more than one. So if you were to again look at it, so some of these connections only appear once, but then other ones are, so there are multiple examples of them. So we want to count how many connections there are between each origin and destination. And for that, we'll use the same tool as the previous week. So week 2, aggregate. Have the line data, yes. And then we'll say that group by the field origin and destination ID. Then remove these individual origin and destination fields. And we'll say that for the ID, take the first value just so it keeps a memory of which connection is being described. And then for the field ID, we say that count, so which I don't know how many connections like this are there. We can call this mobilities or mobilities count. And run. This we have a new layer that has the count of these mobilities. So it tells it, for example, I think from one connection from Spain is the most common one in this year for this dataset. So 18 connections. And this is all actually we need for our purposes. So all that's left is to make, is to stylize this map. So check from properties and make a graduated map. So actually here we'll combine both the color and width to indicate something. So it's in this case from where most of these mobilities come from. Yes, so we can keep these reds. Yeah, or classes. Set mobilities. The value. Yeah, that helps a bit. We also use width to our advantage. And for that, I can rely on data-defined overrides. So from configure symbol and width, we say that instead of using static number, take it from this expression that sort of scales all of the values in the field mobilities to between, so the minimum value is from the minimum value of mobility, so 1, and maximum value of mobilities, and all of the values in between are scaled linearly between the line width of 0.2 and 2.5. And these are, again, sort of arbitrary, chosen by me. So then it scales these line widths smoothly. Okay, all good. Are we getting somewhere? It is still a bit of a bad map, so we'll do a bit. So one wise thing would be to add some transparency. Maybe just eyeball it. Then I think for this one, we'll need some sort of indication, a background map of Europe. And we can add that from the coordinate field, so just type world if you don't have another world map ready. And now we know that something weird happening because of the coordinate reference system that play here. So this is the default one for Finland, which is not great Europe-wide. So I recommend changing that from whatever you have. And a good one would be the one that's also a default for this mobility data layer, which is 3035. 3035. So this is the good one to use all over Europe. Nice. And now we are getting somewhere. Like now we at least see where are the sort of more prominent connections. Now we're really de-emphasizing the sort of singular ones where only one people is moving from. Of course, if we want to improve this map, we could add NUTS to sort of European borders here, or the borders of the NUTS 2 regions here. Yeah, you can see one example of how I visualize this type of graduated map. So using this tool, and then also using the mobility data layer to our advantage, at least label the destinations. And a bit of text buffer, that's always good call. Yeah. So this would be one way we could make sense of this hairball sort of novel approach, I think, which is edge bundling. Say right away that edge bundling is very compute intensive. It's not, there aren't many great tools for it within QGIS. I'll link at the end to some Python and R tools. So this processing might be a task that's best done programmatically. Nonetheless, there is one published plugin that we installed earlier, and we'll run it and see what it does for our dataset. So run it, edge bundling, force-directed edge bundling, and set the original data as the input. You don't need to concern about this cluster here, so leave this unchecked. Then the initial step size. In the instructions, there's an explanation of, at least to my best understanding, what each of these parameters do. And edge bundling is a bit of an art form. It's a bit of fickle. Like the outcome is very much dependent on what these parameters are, what your dataset is. And of course, all of this sort of affects the interpretation that you're giving to the reader. Let's first, when just running this, let's set initial step size to 1000. This basically tells how aggressively the different lines that are moving towards the same direction, how aggressively they are bundled together. So run it, and this will take a while. Okay, so now it's done. You get this new layer called bundled edges. The other ones. So now you can see that, yes, indeed, the original sort of direct hairballs are actually now bundled together so that the lines that are coming, for example, from different parts of the UK are now sort of smooshed together. And in the tutorial text, there's this example of how the impact of these parameters. So, for example, if you were to rerun this whole thing with the initial step size of 10,000, let's see how that looks. And now, indeed, if we sort of zoom in closer, so this bundled edges, and this one is with the initial step size of 10,000. So these edges are really more aggressively bundled together, even further away. So this, of course, affects the outlook of the map quite greatly. And here is a sort of visualized example of how that will look. So this is a neat tool and approach, I think. But we still need some smart styling if we want to make this map useful. And here we could, since we only have 3 destinations, we might highlight where those destinations, or which lines are going towards which destinations. And we could do that with the categorized field with this destination value. And here I chose sort of clearly contrasting colors for 3 of these values. You could use the default ones. You want to change them, which I could, for example, now do. So you can find them in the HTML notation and here. Okay, so now I styled all of them, this orange, violet, and blue colors. Then we could make this opacity of all of these lines or transparency really high. So it's 20% opacity. So now we have added a transparency to these layers. And it's nice for visualizing this because then it highlights the places where those edges are sort of overlapping with each other. So then it de-emphasizes the individual lines and emphasizes the bundles of lines. You could still exaggerate the line width a bit. Set it to half here to make it more visible. And then we'd just go ahead and do the print layout. And see my approach here. Yeah, it's a funky map. Maybe black is too aggressive a bit. Do something like that. Now you should of course then consider which still consider sort of cropping of your map, which map elements to include. At least a title is necessary here. Maybe scale bar, consider those. Then you could compare this align map to the graduated one, this edge bundle map. So what are the strengths of each approach? To just maybe combine them somehow, or when is this map sort of not actually useful anymore? So when would be another type of approach, like the one that's shown in the Python tutorials, like this chord diagram that abstracts away from the whole spatial area and just shows the connections between the places by themselves. When would approach like that, for example, be better than this one? Nonetheless, as I mentioned, edge bundling can, even if the interpretability is not always great, it can still make some really, really nice looking maps. And here I linked to some of the tools. For example, a recently published Python tool that was published alongside this Erasmus dataset. They have some really cool visualization, which I suggest you check out. Some earlier works. There's also some tools for the R language, if you're more familiar with that. There are some ways to go deeper into edge bundling if you're interested in this approach for visualizing flow maps. And with that, I thank you for the week. If you have any questions, please contact me and send a message, for example, through the Discord channel of the course. If you have any questions, if not, then see you next week.